Welcome to The Explainer. Look, today we're going to do something a little different. We are not just going to talk about blockchain, we are going to build one, right here, piece by piece, starting from the fundamental problem it was designed to solve. By the end, you'll see exactly how all these pieces, hashes, blocks, and chains really fit together.
All right, so here's our roadmap. We're going to kick things off with the big one, the double spending problem. Then we'll get our hands on the cryptographic tools that actually solve it. From there, we'll start putting together the blocks and the chain itself. We'll also look at a really clever trick for keeping the whole system efficient, the Merkle tree. And finally, we'll zoom out and see what this all means for a world beyond just digital cash.
Okay, let's dive right in. The double spending problem. The reason you can't just copy-paste digital money. See, the biggest challenge with anything digital, unlike, say, a physical dollar bill, is that you can copy it perfectly. And for decades, that one simple fact was a total showstopper for creating a real person-to-person electronic cash system.
So this is the core question, right? How in the world do you send money directly to someone online without a bank sitting in the middle? This is exactly what Satoshi Nakamoto's white paper set out to answer back in 2008. And the proposed solution was pretty radical. A system built not on trust in an institution, but on trust in pure, cold, hard math. Cryptographic proof.
And this comparison really gets to the heart of it. Think about it. If I have a $20 bill and I hand it to you, that's it. It's simple. You have it now and I don't. The transaction is done. But online, totally different ballgame. We've always needed a bank or a PayPal to act as a trusted third party, to keep a central ledger and make sure I don't send the same digital $20 to you and then turn around and send the exact same file to somebody else.
And that right there, that is the double spending problem. It is the absolute core challenge for any digital cash system. How do you stop this digital counterfeiting, this ability to spend the same money twice, when there is no central referee watching over every single transaction? I'm telling you, the solution to this one problem is the key to this entire technology.
So how do we solve this? Well, the solution begins with a couple of really powerful tools from the world of cryptography. These are what give us our digital fingerprints and unforgeable signatures, allowing us to create uniqueness in a world where everything can be copied. Okay, first up, we have something called a hash function. The easiest way to think of this is as a unique digital fingerprint for data. You can feed it anything, a sentence, a contract, a whole list of transactions, and it spits out a unique string of characters. Now, it's a one-way street. It's super easy to create the hash from the data, but it is practically impossible to go backward. And get this, if you change just one tiny thing in the original data, even a comma, the fingerprint changes completely. It's the perfect tool for verifying that nothing has been tampered with.
All right, so a hash proves that data is authentic, but how do we prove who owns it? That's where digital signatures come in. This is how ownership gets transferred. The owner of a coin uses their secret private key to digitally sign a transaction. This signature then links the hash of that transaction to the public key of the next owner, creating this unforgeable, verifiable chain of ownership that anyone can check.
So we've got our tools, right? Hashes for integrity, digital signatures for ownership. Now let's start building. Let's see how these are used to construct an unchangeable public history of all transactions, a ledger that everyone on the network can agree on. Now, the system doesn't process transactions one by one. Instead, they get collected into a group called a block. You can think of it like a new page in our ledger. And here is the absolutely critical part. Each new block includes the hash, that unique digital fingerprint of the block that came right before it. That is the chain in blockchain. It is what literally links them all together in a secure chronological line. But wait a second, what's to stop someone from going back, changing an old block, and then just quickly recalculating the hashes for all the blocks that came after it? This is where the genius of proof of work comes in. To earn the right to add a new block to the chain, network participants have to perform a huge amount of computational work. It's like forcing them to solve a really, really difficult math puzzle that requires a ton of computing power and electricity.
And this quote from Satoshi Nakamoto really gets to the core of it. Proof of work is essentially one CPU, one vote. In a decentralized network, there is no boss. So how does everyone agree on which version of history is the true one? The rule is simple. The longest chain, the one that has the most computational work, the most proof of work invested in it, is considered the official one. It's a consensus mechanism based on pure processing power.
So this is how it all comes together in this beautiful, chaotic dance. New transactions are just broadcast out to everyone. Each computer, or node, on the network collects them into a block and starts racing to solve that proof-of-work puzzle. The first one to solve it broadcasts their new block to the network. Everyone else checks it to make sure it's valid, and if it is, they add it to their chain and immediately start working on the next block. It's this simple set of rules that allows a secure ledger to emerge without anyone being in charge.
Okay, so our chain of blocks is growing, and it's super secure. But now we have a new problem: data size. As this chain grows with every new block, it could become absolutely enormous. How does the system manage all this data without collapsing under its own weight?
Yeah, I mean, think about this from a practical standpoint. If you had to download the entire history of every transaction ever made just to verify that you received a single payment, the system would be completely unusable, right? It would never work on your phone or your laptop.
The solution here is just so elegant. It's a data structure called a Merkle tree. Instead of hashing all the transactions in a block together in one go, you hash them in pairs. Then you take those resulting hashes and hash them in pairs. You keep repeating this process, kind of like a tournament bracket, until you're left with just one single hash at the very top. That's called the Merkle root, and it efficiently summarizes every single transaction below it.
And this clever structure gives us two huge benefits. First, it allows the network to safely discard old transaction data to reclaim disk space without breaking the integrity of the block's hash. Second, it enables something called simplified payment verification. This means you can prove your transaction is in a block by downloading only the block headers and the tiny Merkle branch that connects your transaction to the root. This is literally the magic that makes it possible to have a crypto wallet on your phone. So, we've built these incredibly powerful tools for a decentralized ledger. But pretty quickly, people realized these same building blocks could be used for so much more than just digital cash. This is where the vision expands from just a payment system to a kind of global, decentralized world computer. And this quote from the original Ethereum white paper captures this leap perfectly. The creators of Ethereum looked at Bitcoin's design and basically asked, what if we generalize this? Instead of a blockchain built just to track transactions of a currency, what if we built a blockchain that could run, well, any program? A platform for any kind of programmable agreement you could think of.
And that leads us directly to the idea of smart contracts. Put simply, these are just self-executing contracts where the terms of the agreement are written directly into lines of code. And because they live and run on the blockchain, they run exactly as programmed, without any possibility of downtime, censorship, fraud, or third-party interference.
You know, this idea actually goes way back. In the 1990s, the computer scientist and cryptographer Nick Szabo laid out the core goals for digital contracts. He said they needed to be observable, so you could see they were performed, verifiable, so you could prove it to others, and have privacy, to keep the details private. Smart contracts on a blockchain are pretty much the ultimate fulfillment of that early vision. So let's just quickly recap our journey here. We started with the problem of double spending. We learned that hashes create unique digital fingerprints. We saw how transactions get bundled into blocks to form a public ledger. We understood how proof of work secures the entire chain through computational effort and how Merkle trees keep it all efficient and verifiable. And ultimately, this entire tech stack is what enables these powerful, programmable, self-executing smart contracts. At the end of the day, this technology is about so much more than just a new form of money. It's a new way to structure agreements, to build organizations, to create trust itself. And the biggest question it leaves us with isn't really about technology at all. It's about what our world looks like when our most important agreements can be guaranteed by code and can simply execute themselves.